that's the time. And I've never been on another side of the camera. So anybody who's watching, if there is a problem with the sound, please send me an email. I will check, and maybe I will make adjustments. Okay? The video, I can see. The video seems fine. I'm not sure about the sound. So, again, we start from a question. Of course, every time we start from a question. And every time a question is about something really simple, like average velocity in this situation. And, well, I'm going to give you a couple of minutes so you would write your answer to this question. Today, I kind of wish everybody would use the response where, because in that case, I could collect remotely all the answers. Maybe next semester. That's going to be a requirement, not sure. The response where is a little bit buggy, so that's why I prefer physical clickers. I guess if a person has a problem to see what's happening here, giving an advice doesn't really matter, doesn't help. All right. Let's hope it's gonna. I'm gonna capture it. Let's hope the quality will be fine. So whoever can see it live can at least see it later. All right. What's your answer? Yeah. Of course. So what's the strategy? Well, we read and we imagine what's happening. Then we have to actually draw a picture. We start here. Travel. Well, we wait and we travel back. And that's the most important part of this situation. When we come back, our final position vector is equal to initial position vector. So according to the definition, there is no displacement because that difference will be equal to 0. For any, no matter how complicated it has been, but for any round trip, the total displacement will be equal to 0. Now, according to the definition, the displacement over time, that gives the average velocity. 0 divided by any number is still 0. Well, what about average speed? Is it going to be equal to 0? No. Time is not 0. Distance is not 0. If you want to calculate the average speed, distance over time, that's going to be 3 kilometers one way plus 3 kilometers back over 40 minutes one way plus 20 minutes layover, plus 60 minutes inside, back, so 6 kilometers over. That's going to be 120 minutes, which is 2 hours, 3 kilometers per hour. Again, just to illustrate the difference between average speed and average velocity. Well, we started talking about one-dimensional motion. These are most important cases of one-dimensional motion. Again, the case number 1, resting object. The case number 2, the object travels with constant velocity. Case number 2, the object travels with constant acceleration. I wanted to show how to use this software for your lab. You're going to use it for the lab number 2 anyway. So rest. If we want to look at the graph for velocity, what should we see? 0, 0, 1, 2, 3, -1, -2. Of course, there is no velocity. The slope of this line is 0. A horizontal line for the graph, for the position as a function of time, means there is no motion. Now, I'll try to move it with constant velocity. And well, we can stop. Now, let's increase both. You see that right now, so the velocity was 0. This is a very noisy situation because probably my sleeve was in a way. Yeah, this is a ultrasonic sensor emitting ultrasound pulses and collects it back, and that's how it measures its position. So if something is in a way, it obstructs the beam. But here we can see, where is it actually? No. The velocity graph is very noisy. When I started moving this cart, it was, the velocity was going up from 0 to a certain value. But graph of velocity as a function of time is not very informative because of the noise. What can we do? Well, we know that the slope of this line is supposed to be equal to velocity. So all we have to do is just calculate or measure that slope. And if you use this software, you can just click on linear approximation. And what you see is a linear function, x equals m times t plus b, a standard equation for any linear function. What does m mean? That is the slope. So if you read m equals 0.1919, that means that's your actual velocity between, well, this instant and that instant, like from 1, 2, 3, between 3 and 5, right? And, okay, one more example for the motion with constant acceleration. I want to see if that's not going to be noisy. So now we can see 3 graphs. Of course, I need to start again. Let's see if I'm going to be quick enough. Oh. Got it. Stop. So that was almost, well, less than a second. Where was it? Well, you see here we have a very smooth, well, that's a parabola. That's not a straight line anymore. So what can I do? I can select this particular segment of the graph. I can actually, I don't know. I just want to stretch it first a little. Now I want to select it. Now I can make a fit, quadratic fit. One quadratic, okay. So what do we see? We see a quadratic equation, time squared, time, and constant. These 3 constants, A, B, and C, have a very important meaning, and we'll talk about later, of the meaning of each variable. But now we just need to remember that, well, when we talk about one-dimensional motion, these 3 situations can be differed, distinguished, separated by the graph for the position as a function of time. Of course, in real life, we might have something more complicated. The next step is analyzing a motion which has several parts. Yeah. When you're driving, for example, you start motion from rest, so you're speeding up. Well, you can assume that you keep your acceleration constant. Then you reach velocity you want to keep, and then you travel with constant velocity. Then you may be slowing down. So in that case, to analyze the whole motion, you may apply different parts of different equations. And in general, of course, the motion might be so complicated that the equation is neither linear nor quadratic. That's something beyond the scope of this course. Velocity. We know two velocities, average and instantaneous. If we have a graph for the position as a function of time, what do we do to get the average velocity? Well, according to the definition, it should be displacement over time. So, what do we have here? Two instances, initial time, final time. This is the initial position. This is, we read here, the final position, final coordinate. How do we calculate the displacement? This is the displacement, delta x. The time of the travel, this, delta t. So, in math, you call it rise over run. Rise over run. That gives you the slope of this line. That gives you this coefficient m. And that's what should be equal to this average velocity. So the average velocity also can be read from the graph. It's just the slope of that line which passes two positions, initial and final. And here, if the graph is complicated, and we want to figure out now instantaneous velocity, what do we do? Well, as you know, we should consider two locations which are very, very close to each other. In this situation, the slope of the line which is tangent to the graph will be equal to the actual value of instantaneous velocity. So here, we can ask the question, what's velocity, instantaneous velocity of the object when it was traveling through x equals, well, negative 2.7, for example. So in that case, we should draw a tangent line and measure or calculate its slope. That will be instantaneous velocity at that instant. Any questions? You actually should ask questions if you have it, since you're here. I have one more email. Maybe. MCV. I've got a question. So, motion with constant velocity. MCA, motion with constant acceleration. All right, let's elaborate. What do you think? What is instantaneous velocity at, well, call it time TD? Is it positive? Is it zero? Is it negative? Yeah? We should draw a line tangent to the graph and look at the slope. That's the positive slope, positive velocity. Well, here, that's going to be the negative slope, negative velocity. What about this instant? No slope, no velocity. Instantaneous velocity equals 0. It was not equal to 0 before, and it is not equal to 0 after. So how do we call it? Well, let's see what is actually happening here. From point A, according to our agreement, where is my ruler? The positive x direction always points to the right. Always points to the right. So that's my ruler. From 0 to the right we have positive numbers, to the left we have negative numbers. This is my cart which is traveling, and when we look at it, it actually doesn't travel like this. No. That's not a photograph of the motion. This is not a trajectory. The car is traveling, well, either to the right or to the left. It's a one-dimensional motion. But if we read every time its coordinate, its position, and we plot a graph, that's what we might see, all right? So here, at the very first instant, A, how was it traveling? To the right or to the left? To the left, because that's what the velocity is, yeah? So if the slope is negative, that means this is a negative number. Well, I say velocity, velocity, but the full name is the x component of instantaneous velocity. Yeah? And if it's negative, that means the vector which represents the instantaneous velocity points to the left, because it has to point opposite to the positive direction. That's it. So here, at this point, I, the velocity is a vector. The slope is positive, means velocity is positive. That's not a vector. Yeah. So this component is positive, which means the actual instantaneous velocity vector should point to the right. Any questions? And what was happening here, it was traveling to the left. Here, it stops instantaneously, and then it travels again to the right. So that's what we call the point of return, or reversal. It reverses its direction. And then again, it's happening again. At point E, it stops momentarily and now travels to the left, etc., etc. That's how we read the graph, and that's how we match the graph and the actual motion of an object. Any questions?
Attention, please. In a second, you will see a good example of how our brain plays tricks on us. The screen clearly says motion with constant velocity, but twice I said motion with constant acceleration before I corrected myself.
So as we said, for the motion with constant acceleration, the position graph is just a straight line. Not every time goes up, it could be down. Yep. And for the motion equation, this is what we should write. For any motion with constant acceleration, this is always the motion equation. Let's apply this knowledge to this graph.
Sorry, can I see that motion equation?
Well, you see, as we know, for the motion with constant velocity, it has to be, this graph has to be a straight line. We know from math, any straight line is being described by the linear equation. So this equation and the motion equation is the same equation. It just, in physics, these variables have a special meaning. That's what we call the slope, which is instantaneous velocity, which equals to average velocity if velocity stays the same constant. And that's, well, in math, how did we call this number in math? Y-intercept, yeah. But in physics, this is actually the initial coordinate or initial position. So basically, this is how we merge mathematics and physics. It's the same equation, absolutely. On top and on the bottom. It just, in physics, these variables have a special meaning and name, and we need to know those names. Yeah. All right. So, too many questions. I'm going to talk about a couple of them. First of all, I would always start from the motion equation. So if you want to find instantaneous velocity at t equals 10, so this is what you should do, right? T equals 10 here. Here, you need to calculate the slope of this line. How do we do that? Well, from here to here, the slope is the same, doesn't change. So, for example, what we can do is just calculate the tangent of this angle. That's going to be the velocity at t equals 10, as well as at t equals 9 or 18, because the velocity is constant between t equals 0 and t equals 20. So what do we do? Well, this is delta x. This is delta t. And that's going to be 100 minus 50 over 20 minus 0. That answers our question. We just need to remember that we need to understand that this graph represents motion with constant velocity, which means velocity stays the same between 0 and 20. So we don't really know yet what would be the actual value of x at t equals 10. If we knew, we could have used this little triangle to calculate the velocity. But since we don't know that value, and we don't have very clear grid, we don't have very clear reading, we cannot use that value. So that's why we extend the triangle using the fact that velocity is the same everywhere. Now we can write the motion equation. Please write the motion equation between for time interval between 0 and 20. So the motion equation that's supposed to be, what number should we write for m, for the slope? $50 over 20, 2.5, right? 2.5 plus. And this, again, should be the initial position for this time interval, which is 50. So that's our motion equation for any t between 0 and 20. Now if we want to, we can actually calculate the exact value of x at t equals 10. We just have to plug in this equation, t equals 10. Oh, sorry, I miswrote. Any questions? And I want to all right, let's do these two. No. This and this. Again, average speed and average velocity. For the average velocity, x final minus x initial, t final minus t initial. So between 0 and 50. Well, 50 minus 0, that's what we should write at the bottom. What should we write at the top? At t equals 50. Oops, what happened? What happened? At t equals 50, x equals what? 0. So the, what's it doing? I don't know. It's alive. So the final value for x is 0. What? At t equals 0, x was equal to 50. So what do we get? Negative 50 over 50. That's the average velocity, negative 1. Can average speed be negative? No. Distance over time, distance is never negative. Tricky part is how to get the distance. Well, now, like we just did 5 minutes ago, we have to match the graph and the actual motion. So it starts from 50. It moves from 50 to 100. How many meters did it move? 50. Then it rests for 10 seconds, and then it goes from 100 back to 0. Back to 0. So now, how many meters did it move on its way back? 100. So what the total distance traveled? And that's why the picture worth 1,000 words. So what I want to do is kind of a movie of what was happening. It starts from here, and it goes to the right, reaches 100, rests here, and then it goes back from 100 to 0. So it travels L1, 50 meters to the right. Then it travels L2, 100 meters to the left. So what's going to be the total distance traveled? 150. Exactly. And now, of course, the rest is simple. The average speed is supposed to be total distance over total time, supposed to be 150 over 50, 3. Any questions? Moving on. Now, you see a different set of axes, velocity as a function of time. Well, in general, it could have been anything. for the motion with constant velocity, that should be a horizontal line, constant. But in general, anything like this curve, for example. What information can we extract from this graph? Well, if we solve the definition of instantaneous velocity for the displacement, yeah, we can apply this equation to many, many consecutive displacements. That's my initial time. Then a fraction of a second later, my final time. So this is my velocity at initial instant. This is my delta t number 1. Now please tell me, if you multiply this and this, what does it give you? The area of this rectangle. So then you can apply the same reasoning to the next tiny displacement, and that will give you the area of the next very, very narrow rectangle. Next, etc., etc., etc. So that was displacement number 1. That was displacement number 2. And if you add all together, etc., to the last tiny displacement, number, I don't know, n, that will give you the total area covered by this curve. So the fact, very convenient and very important sometimes, is simple. If you have the graph for velocity as a function of time, the area covered by this graph is equal to the total displacement. Total displacement equals area. Well, what I just said now is written, so one more slide which says exactly the same thing again. So it's imprinted in our brain now forever. For the graph, for the position as a function of time, the slope of the tangent line is equal to velocity. On the graph for velocity as a function of time, the area covered is equal to the displacement. Quick example. Here we have the graph for velocity as a function of time. Don't read the questions. Let's just walk through the problem. I want to enlarge the graph. Velocity time. How do we call this motion? Again, we have 4 names in general. We could call it rest. We could call it motion with constant velocity. We could call it motion with constant acceleration. And we could call it anything else. So that line represents what kind of a motion? Constant velocity. See? V, velocity. 15 miles per hour, 15, constant. So this area represents the displacement from t equals 0 to t equals 45 minutes. That's it. That's what we call displacement. Well, if you look at the graph, we can see that this total motion is composed of 3 individual parts. The part number 1, 45 minutes. The part number 2, 15 more minutes. The part number 3, 60 more minutes. So total displacement for the part number 1 will be equal to, well, 15 miles per hour times 45 minutes. It's actually easier to use hours in this situation. 15 miles per hour, 45 minutes, that's 3/4 of an hour. Times 3/4 of an hour. So 15 times 375 divided by 4, whatever, 75, 4 miles. That was the total displacement. Next part. 15 minutes. What was happening for 15 next minutes? Nothing, rest. Well, if it's a question about a bicyclist, that guy was riding a bicycle, then decided to take a break, that's it. And what was happening for the next hour? For the next hour, see the actual value of velocity, which is another name for the x component of velocity, is negative. So this guy has been traveling back. So what was the displacement now? Well, again, the magnitude of the third displacement should be equal to the area of this rectangle. So it has to be equal to 20 miles per hour times 60 minutes. 60 minutes is 1 hour, so it's going to be 20 miles. But that's the magnitude. If I want to ask you, what should you write for the actual displacement? What should you say? Negative 20. So we can draw the displacement number 1 that points to the right. We can draw the displacement number 2. That dot, this dot, represents the displacement number 2, rest. And we can draw the displacement number 3. And now we can answer all possible questions. For example, what will be the total displacement? Well, it should be this plus this. So it's going to be a short arrow pointing to the left. And what will be the magnitude of that arrow? The magnitude can't be negative. So it should be 75/4 minus 20 magnitude. If you say, what did you say? 1.25. What's your number? I need a confirmation from a second fellow student. In that case, I can put it on the screen. All right. Agreed? Any questions? All right, moving on. So it's solved.
Hello again. Did you see the mistake I've made in the beginning of this calculation? This is another good example of, well, the fact that sometimes brain does play tricks on us. My eyes see 15, but my brain thinks 25. 15 times 3, of course, is not 75. It's 25 times 3 is 75. 15 times 3 is 45, clearly. So the calculations, starting from this moment, are wrong. But the strategy was correct. So at least I got a partial credit.
Now, we'll talk about relative motion. As we know, any motion is relative. For example, a passenger on an airplane or on a ship, the plane travels relative to the ground. So every passenger sitting travels relative to the ground with the same velocity the plane travels. But what if somebody is walking inside the plane? Well, in that situation, we get a slightly different and slightly more interesting situation. This piece of paper might represent a lake, a plane, a river, a ship, anything which can move relative to the ground. And this card might represent a person walking on a plane or a boat traveling in a lake or in the river. So let's say this is the plane. Use your imagination. And it's on the ground, not flying. And this is the person walking inside. So in that case, this is the displacement of that person relative to the airplane. And this is the displacement of that person relative to the ground. This is the ground. Do you see it? Yep. So the displacement of the person relative to the plane is equal to the displacement of the person relative to the ground. Now let's make this plane fly. This will be the displacement of this person walking inside the airplane relative to the airplane, right? Now this is the displacement of the airplane relative to the ground. Any questions on that? So in that case, this will be the displacement of that passenger relative to the ground. And relative to the ground means we always can imagine an actual person sitting here and looking at this, well, passenger or wherever it is, and another person who is on the ground and has ability to look through the plane. So that person sees the same walking passenger. So two origins. Yeah? So we can immediately conclude that the displacement of this passenger relative to the plane plus displacement of the plane relative to the ground should give us the displacement of this passenger relative to the ground. Now, of course, we should write this statement mathematically, in the mathematical form. Well, we use standard symbolism. Delta R represents displacement. So this is how we can read it. The displacement of the passenger relative to the ground is equal to displacement of the passenger relative to the plane plus the displacement of the plane relative to the ground. Now, we have to remember two things. Number one, the displacement is a vector. So this equation works for any situation. It doesn't matter how the passenger walks. It can walk to the right, it can walk to the left, across the plane, it doesn't matter. The equation stays the same. Number two, nature doesn't care about the actual objects. Is it a passenger or a boat in a river or something else? These are just objects traveling in space relative to each other. And how many objects do we have? 1, 2, 3. 3 objects. We don't have to call them passenger, plane, ground, or boat, river, and shore. No, we can just count them. The object number 1, number 2, and number 3. Ground, plane, passenger. In that case, this law describes the relative motion in any possible situation. How do we read it? The displacement of the third object relative to the first object is equal to the displacement of the third object relative to the second plus displacement of the second relative to the first. It's very easy to remember. Oops. What did just happen? You're basically just inserting 2 2's inside, between 3 and 1. 3, 2, 2, 1. In an actual problem, we always can assign the actual meaning to each object. In this situation, I called the passenger the object number 3, the ground the object number 1, and the plane the object number 2. But, of course, it doesn't matter. I could have called the ground number 3, the plane number 1, and the passenger number 2. This law doesn't change. And before we're moving on, there is another very, very common situation when we talk about relative motion. A boat in a river. Now, the same paper represents, well, at first, let's say it represents a lake, and this is the boat. Shore. Again, the displacement of this boat relative to water is equal to the displacement of this boat relative to ground. Of course, that's not going to be a case if this is a river, because the river has a stream, it flows. And, well, let's say you do again something like that. Same case, the displacement of the boat relative to river plus of the river relative to ground. And you can always imagine there is a raft. Yeah, that's the boat. There's an engine makes it move. And there's a raft which just travels with the speed of the stream. So the displacement of water relative to ground is basically the displacement of that raft relative to ground. If you add them together, that gives you the displacement of the boat relative to ground. What if the boat aims, well, let's say at 90 degrees to the stream? We start here. Where is it? It's kind of dark. Better, better. So, do we see red? Red. Do we see yellow? Yes. Again, if it's a lake, I don't want to let it. Yeah. So if it's a lake, of course, it reaches the opposite shore exactly across the initial position. What do you think is going to happen if it's not a lake, if it's a river? You get an idea, right? So that was the initial position. And now this is the final position. This is the displacement of the boat relative to what? What do you think? That's the most important question now. Again, we have three objects: river, boat, shore. And we have the displacement of the boat relative to the river. And we have the displacement of the river relative to the shore. And we have the displacement of the boat relative to the shore. And if we match them correctly, done. We know everything about relative motion. So now this is the matching situation. This arrow, what does it represent? What kind of a displacement? Now I'm going to finish. This is a different situation. So this was traveling with the river. That's displacement of the boat relative to the river. If a person was sitting here in a chair and looking at the boat, this arrow represents the displacement of the boat relative to the ground, relative to that person. And this arrow represents the displacement of the raft of water relative to that person. And we can see again, they form a triangle. The final displacement of the boat relative to ground is equal to the displacement of the boat relative to water, displacement of the boat relative to water, plus displacement of water relative to ground. All right, and just one last word. Displacement over time is velocity. So that's the law we need to know because we're going to apply it on Thursday and on Friday when solving a problem, in a discussion problem. The law of relative velocities. The velocity of the third object relative to first is equal to the velocity of the third object relative to the second plus velocity of the second relative to the first. The actual nature of those objects don't matter. Doesn't matter if it's a boat, a plane, or ground, or bush, or a cloud, or anything else. Now we're done. Thank you. Any questions? So I'm going to post these notes online. I'm going to check if everything captured. And in that case, I'm going to post the movie online. And we'll see how it goes. Thank you for watching. Send me a question if you have it. Hmm?
How are you going to take attendance for
Everybody already, yeah. It's automatically done. Yes.
So I was watching this live for class, so I kind of sprinted over here because I couldn't understand anything you were saying on the live stream. I don't know if that's a thing. I don't know.
I wish you would.
That's what I was in my dorm. And
I wish you would told me in the beginning. I might have tried some.
I don't know if it was just like at that moment.
I don't know either. You know. So, but let's hope the video will be fine. In that case, everybody will be able to hear it. The problem with using streaming software on every computer, it requires some adjustments depending on what you use in Mac or Windows, which version. So I used my, if you have a cell phone, you can actually watch the streaming on your cell phone. You just need to upload the app. It's free. And when I was checking it today, the sound was fine. So I'm not sure.
It must have just been my Mac.
We'll see. On Friday, I'm going to have many complaints, maybe.
I also have one more quick question. So I
Yeah.
logged website to look at the homework. And, we had the 3 surveys that we needed to complete.
Yeah.
But, all the other homework assignments have been due. I don't know, like.
This is how. So you read the problem and it rings the bell. You've seen something similar.
Right.
So you solve it. You read the problem and absolutely, something absolutely new, it means we haven't covered it yet. So just wait.
So WebAssign doesn't do like weekly deadlines. You just
My website doesn't do that. I could have broken all assignments like on a weekly basis, close one, open another. And I've done it before. But this time I don't do it. It's not going to be any more new problems. It's all.
Okay.
No new problems.
So we just go
Yeah.
weekend.
Yeah.
Okay. Great. Thank you.
Yes. Well, for that particular answer, we need to see the picture. And north of east, that's what you want. This number cannot be more than 90 degrees. If you measure north of east, that means you start from east and you go to north, and this is going to be the angle. So 331 is just, it might be actually a correct angle, but it's not not the number you need to enter. You need to see your picture. And actually, I think that is the correct number if you measure it that, for example. You can send me a picture. I can look at it. This is relative to the ground in this situation. We have two displacements.
Yeah, we have from where it was before and
Yeah, well, two objects change its position. Water changes its position relative. And the boat changes its position relative to the ground. Boat relative to the ground. So imagine that you are on the raft here, and you're looking at the boat. In that case, the boat will be traveling directly away from you. So this will be the displacement of the boat relative to you, which means displacement of the boat relative to the river. And if we add them together, river relative to the ground plus boat relative to the river, that gives us displacement of boat relative to the ground. Просить вас, как